Usually when we think about precision engineering, we picture these sterile labs, microscopes, lasers, everything kept at exactly room temperature.
Right, yeah. But in reality, inside the transmission of a high-performance machine, well, precision is actually forged in a literal crucible of fire. Fire, crushing physical constraint, and, deep freezing.
Yeah, so today we're tracking the absolutely brutal journey a chunk of metal takes to become a flawless gear. Because if you have ever wondered why your car's transmission doesn't just shred itself to pieces on the highway under immense pressure, well, it comes down to a microscopic battle fought with extreme temperatures.
Exactly. I mean, the materials have to undergo a tremendous amount of stress before they can reliably handle the forces of actual operation.
Right, so the journey begins with fire, specifically a process called case hardening or carburizing. The goal here is to create an outer, hard, inner, tough structure, right?
Right. They want the gear to hit HRC 60, hardness for wear resistance, which, to put that in perspective, means the surface is essentially hard enough to scratch glass.
Oh, wow. Scratch glass. But if the entire gear were that hard, wouldn't it just, shatter like glass on the first heavy impact?
Exactly, yes. So you need that soft, impact-absorbing core. It is the toasted marshmallow approach. Crispy on the outside, soft on the inside.
I love that. A toasted steel marshmallow. But getting that crispy exterior requires heating the metal and then cooling it incredibly fast. And that introduces a massive problem, right? Quenching distortion. Is that just like a cheap plastic container warping in a hot dishwasher?
Well, it is a bit more intense than that. When metal cools rapidly, its atomic structure actually shifts and expands. It is similar to how water expands when it freezes into ice inside a closed pipe.
Oh, I see. So it expands and pushes against itself.
Yeah, exactly. Those internal structural shifts literally bend the metal from the inside out. It is one of the hardest errors to control in precision manufacturing.
So it is not just heat making the metal soft and melty. We are fighting the metal's changing atomic geometry as it tries to tear itself apart. How do you even fix that?
Well, engineers have to deploy highly targeted solutions to stop that internal sabotage. One method is tempering. Instead of a rapid, chaotic cool down, you drop the gear into a constant temperature, hot salt bath.
Wait, a hot salt bath. So you were essentially hitting pause on the cooling process.
Precisely. It gives the atoms time to arrange themselves into a highly stable structure, which we call bainite, rather than panicking and, warping into random shapes.
Right, okay, that makes sense. And that stability is why tempering is crucial for heavy-duty components like those cycloidal discs. But what happens when you have a piece that is incredibly delicate, like a thin-walled ring gear? You can't just drop that in a bath and, well, hope for the best, right?
No, you really can't, because it naturally wants to warp out of a perfect circle as it cools. So the solution there is press quenching. They physically clamp the hot gear inside a rigid mold while it cools down.
So they just force it, and it sounds like putting a rigid mechanical corset on the metal. Are we just forcing the gear to behave against its natural will to warp?
We absolutely are. Mechanical constraint during these violent structural shifts is indispensable. By press quenching, sheer physical force is being used to override the metal's natural tendency to deform.
Wow. You are literally locking it into perfection while its internal structure settles. That is intense.
It is, but we are actually not done yet.
Right. Which brings us to the most surprising part, because it seems completely counterintuitive that after baking a metal to harden it and clamping it to shape it, the final step to stabilize the whole thing is dropping it into a cryogenic deep freeze.
What?
Wait, really? We just baked and clamped it and now we are deep freezing it. Why does extreme cold fix what extreme heat started?
Well, it fixes the hidden microscopic flaws left behind by that extreme heat. After the carburizing and quenching phases, you are left with something called retained austenite.
Retained austenite. Okay, what is that exactly?
It is a phase of the metal's crystalline structure that just didn't fully transform during the initial cooling.
Meaning it's fundamentally unstable at room temperature.
Exactly. If you just leave it there, over years of friction and stress inside an engine, that austenite will eventually try to shift. And that would subtly warp the gear over time.
Oh, wow. So by dropping the temperature to cryogenic levels, you basically force that stubborn leftover austenite to finally complete its structural transformation.
Yes. You are eliminating the microscopic instability once and for all to lock in long-term dimensional accuracy.
Which proves that macroscopic stability, a gear running flawlessly for a decade, is ultimately won at the atomic level.
A true crucible. The microscopic battles are what win the macroscopic war.
Incredible. So we've tracked the brutal journey of a precision gear. It survives the carburizing heat, it is physically forced into its shape during press quenching, and finally, it is subjected to a cryogenic deep freeze to stabilize its very atoms.
Right. And it does all of that before it ever turns a single wheel.
So true. So the next time you hear a smoothly running engine or a perfectly quiet transmission, think about the immense, invisible forces locked inside those gears. It makes you wonder, what other perfect systems in our world are only holding their shape because they were forged under extreme constraints?